Today's topic is the Laurent transformation, also called the Z transformation. First, let us recall the definition and all the properties of the Laurent transformation. If someone already has a script, it will be convenient to have it close by. First of all, I would like to draw attention to the nomenclature, because it is possible that I will often get confused in this matter. Please remember that a transformation is an action that results in a transform. The Laurent transform is the result, and the Laurent transformation is the action that brings us to the result. By definition, the Laurent transformation of function f of ntp is equal to the sum, with n equal from 0 to infinity, of the values of function f of ntp times the complex variable z to the power of minus n. The basic properties are linearity and uniformity, which are rather obvious. The transform of the sum is equal to the sum of the transforms. And if we have a transformation of the function times a certain constant, we can take this constant before the transformation. A few more words about the function f of ntp. It is a discrete time function, that is, it takes values only at specific moments of time, where n is the time step number, we count it from 0, and tp is the sampling time. Why tp and not ts? Because I don't want to change tp to ts everywhere. If you want, you can write ts, but I will write tp. Just remember that this is a capital T with a subscript, because it happened to me that someone tried to shorten only the capital T. The Laurent transformation itself is in some sense similar to the Laplace transformation, but the latter is for continuous functions, and we will now deal with discrete time functions. Other properties include time shift, multiplication by n, and change in complex scale z. In the first case, to use this property, we must have a properly prepared function that we want to transform. The power at z indicates how many samples the function lacks. In the second case, it is only the simple derivative with respect to z to calculate. One just needs to remember about the minus sign. The complex scale change property is shown in 3 versions because we will typically use it for the case shown in the first line, but the general formula is given in the second line. Any type of tasks may appear during the test. The notation f of z by a means that in every place where z would normally be, z should be replaced by z by a. That is the entire expression in brackets. And in each of these cases, we use f of z, where f of z is the Laurent transform of the function f of ntp. The next property concerns the periodic function. If we want to calculate the Laurent transform of a periodic function, we first need to calculate the Laurent transform of the first period of the function, and then we should use the presented formula. The small p in the denominator denotes the length of the period, that is, the number of samples. And these are the last 2 properties. The first one allows us to calculate the initial value of a function in the time domain using a function in the domain of a complex variable, f of z. The second one allows us to calculate the final value in the time domain. However, in the latter case, we must first check whether the poles of the product 1 minus z to the power of minus 1 times f of z are exclusively inside the unit circle. If not, then the final value does not exist, and if so, you can use the given formula. This was the theoretical introduction, and now let's try to use the learned properties in specific calculation tasks. First, let's calculate the Laurent transform of the unit step function. Therefore, our function f of n tp is equal to 1 of n tp. Every time the number 1 appears and there is an open bracket right next to it, I assume that we are dealing with a unit step function. If we want to multiply the bracket by 1, we need to put a dot between them. What does the discrete time unit step function look like? This is the value 1 in subsequent steps, starting from 0. Before the 0 step, the value is 0. So, by definition, f of z is equal to And what is the value of the unit step function? It is 1 for each time step, for each n. Let's write down the first few components of this infinite sum. We have this infinite sum. We see that each subsequent term is divided by z, which means that the subsequent components of this sum form a geometric sequence. The sum of an infinite sequence is called a series. So we need to calculate the geometric series. For this purpose, we will use the formula where a1 is the first term of the sequence and q is the common ratio between adjacent terms, and more specifically, by how much the previous term must be multiplied to obtain the next one. Our first term is 1 and q is equal to z to the power of minus 1. This is the transform of a unit step. Now our task will be to calculate the Kronecker impulse function. The Kronecker impulse is denoted by delta of n tp. What does this discrete signal look like? it is value 1 in 0 and 0 otherwise. By definition, f of z is equal to so we see that the result is 1. In the next task, let's assume that our function b of n tp is n tp. Therefore, it is linearly increasing function. tp to tp. And now, what should we call a function that depends on the variable z? This will be b of z. Let's use the definition once again, because unlike the Laplace transformation, in the Laurent transformation the ability to count by definition may be useful. So, what to do with it now? The subsequent terms do not form a geometric sequence. At the beginning, let's put tp in front of the bracket to make it easier to look at. Let's enter such terms here to obtain a geometric sequence. But we still have 1z to the power of minus 2, 2z to the power of minus 3, and so on. Well, let's write the second sequence. Now we have 1z to the power of minus 3 left. So and so on. We use the series formula again. The second sequence starts with z to the power of minus 2, let's take the denominator out of the brackets. And now we have another series. And finally, the result is I encourage you to remember this result and the two previous ones, that is, unit step transform and Kronecker impulse transform. Because thanks to this we will be able to significantly speed up calculations for more complicated tasks. The next task is given in the form of a graph. And our task is to calculate the function that is the transform of d of ntp. On this occasion, I would like to draw your attention into two issues. First, the notation of the result. The result cannot hang in the air. The result has to be assigned to something. If the task contains calculate the transform of a function, we can write or something like that. We can also use the notation of this function in the complex domain, d of z. However, if the content of the task is, as now, compute a function that is a transform or a function in a complex domain, then the answer must be marked as d of z. The second thing you have probably already noticed is the changed letter. When describing a function in the time domain and in the complex domain, we use exactly the same letter. Only in the time domain it is lowercase, and in the complex variable domain it is uppercase. However, before we move on to the result, we need to write the function in the time domain. First, let's consider what component functions our function d of ntp can be composed of. The first component is the unit step function, but multiplied by minus 2tp and the light by 2tp. Now, what function would we have to add so that the sum gives us the function for which we want to calculate the transform? It will be a linearly increasing function starting after 5tp. Why does it start after 5tp and not after 6tp? Because the linearly increasing function starts at 0tp. And we need to add both of these components together. This minus 2tp in the unit step argument causes a delay of 2tp. This is obvious when we notice that for n equal to 2, the unit step argument is equal to 0, and for smaller n this argument was negative. Therefore the unit step function value was 0. And now the second component. One must designate straight line formula. First, the slope coefficient, that is, the tangent of the slope angle, which here is equal to 1. The variable is ntp, and the intersection with the vertical axis is at minus 5tp. And we need to multiply this entire function by Why did we multiply by this? Because this component is, in a sense, a discrete time ray, and it starts after 5tp. And we see that for step n smaller than 5, the argument will be negative. Therefore, this will reset the written formula to 0 for n smaller than 5. Calculating the transform, we will use the time shift property, which I remind you. Well, so what do we have to do here? It turns out nothing. To apply this property in simple words, both brackets must be the same. In the second case, they already are, while in the first case there is no second bracket. But if a given component consists only of a unit step, then it can be multiplied by a unit step of the same delay, as this will not change the value in any way. Of course, you don't have to write it this way, but I want everyone to see why you can also use this property in the first component. We can therefore proceed to write the result. The transform of sum is the sum of the transforms, so each component can be considered separately. Minus 2tp is a constant that can be taken before the transform. And the lie is 2tp, therefore. And finally, one needs to multiply by the transform of the non-delite function. In our case, this function is unit step, the transform of which we should remember. We write the second component similarly. The constant is 1, so we don't have to write it. The delay is 5 samples. However, in this case, our non-delite function is ntp, and we should also remember the transform of the ntp function. If the task states that the result should be on one fraction line and segregated by powers of z, then the result needs to be converted to this form. The result segregated by powers of z means that there cannot be any multiplication of variables z in the denominator and numerator, and z to a certain power can only occur once. That is, if it occurs more than once, it should be taken out of brackets. The order of the powers of z is not important. And this is the result. And again, we are dealing with a graph that needs to be decomposed into half-line components. Starting from the left side, we add subsequent components, one by one. The first component is a constant value, free TP. We see that after time 3tp we need to add another half line, such that the sum of both of them consists with the function r of ntp. How much do we have to add to 3tp to get a total of 0tp? Minus 3tp. And how much do we have to add to 3tp to get minus tp? Minus 4tp. This is array, so the other points are obvious. I know that adding subsequent points is much more time-consuming than simply drawing a straight line. Therefore, if someone prefers to use solid lines at the stage of decomposition, it will not be a problem for me. Just remember that the values are only specified for multiplies of tp. The sum of both components stop matching after 7tp, so another component must be added. After time 7tp, I have components with values 3tp and minus 7tp, which gives a total of minus 4tp. How much do I need to add to get minus tp? Exactly 3tp. We already have 1 point of the array. We need one more, so let's count it for time 8tp. The sum of the first two components is minus 5tp. So how much do we have to add to get 1tp? 6tp. So we have another half line. But please see where the point of this array would be if it started after 6tp. It would be exactly 0. That is, adding this point will not affect the result. So this third array starts here or here. It turns out that in both cases we will get the same result. I assume that the third component begins after 6tp, but I encourage you to perform calculations for the array starting at 7tp. Unfortunately, after 10tp it no longer fits, so we have to add another last component. Perhaps some people already know how to quickly calculate the sum of the first three rays after 10tp, but I will do it one by one. The first component is 3tp. The second component is minus 10tp. And what is the value of the third component after 10tp? That is 12tp. Adding this together, we get a total of 5tp. How much we must add to get minus tp? Minus 6tp. We now need to do exactly the same for time 11tp to obtain the second point of this half line. The sum of these three half-lines is 7tp. How much do I have to add to get minus tp? Exactly minus 8tp. So I have all four components. At this stage it is a good idea to write all the formulas of this race. In the first case it is a constant value of 3tp. In the second case, we have a decreasing function, so the slope will be negative. The tangent of the slope angle is tp by tp, which is 1. Finally, the slope is minus 1 and the variable is ntp. And where would be the intersection with the vertical axis? In this case, in 0. So there is no need to write it, but for better readability, Okay, now the third component. The slope is 3. And where would be the intersection with the vertical axis? At minus 18 tp. And the fourth component. The slope is minus 2. And the intersection with the vertical axis is at 14 tp. It took some time, but if you practice, it will go much faster. And now we will write the entire function r of n tp. First the function value, then the delay. It was no delay here, so the 1 of ntp could be omitted, but in subsequent cases this unit step is necessary. This is the analytical form of the function r of ntp. We will use the time shift property again, but this time we do not have a situation where both brackets are the same. In order not to write the entire function each time, I will focus on individual components of the function r of ntp. The first component. As I already explained in the previous task, if I only have a unit step, I do not need to transform anything here. The second component. And now we need to perform a number of transformations to obtain components for which we can use the timeshift transformation property. Please remember that we can only perform modifications for function part. However, we cannot modify the unit step. It must be the same throughout all equations. At beginning, one need to take the parameter next to the ntp variable out of the brackets. In this case, it is minus 1. In the next step, let's write in brackets what we would like to receive. That is and now we need to add something so that everything mathematically matches. So we need to add 3 tp. In the last move, we need to break the bracket into two parts. The first part will contain ntp minus 3 tp, and the second part will contain plus 3 tp. And now we are able to use the time shift, because in the first case we have two identical brackets, and in the second case there is only a unit step with a constant. Third half-line. We start by taking the constant at ntp out of the brackets. And we see that this was enough. Both brackets are the same. And the last ray. The constant goes in front of the bracket. Let's write what we want to get in brackets. And now, to make it mathematically correct, I have to add plus 3tp. We break the bracket into two brackets. Now a few words for people who have already understood this and want to go deeper into the issue. The others can stop listening for a few moments. I call this method of bringing a function into a form in which it is possible to use the time shift as a mixed method, because you need to do something both in the drawing and in the transformations. With the graphical method, we would have to draw a little more on the graph, but the subsequent transformations would be simpler. And the third method, the analytical method, I will show in the next task. The graphical method requires that each increasing or decreasing component starts on the horizontal axis. Therefore, for example, the fourth component should be decomposed into two such components. The horizontal ray is minus 6 tp, which is, when we look at the result of the transformations, exactly what we obtained after calculations. Okay, I've finished speaking for more advanced. Now everyone listen again. We can proceed to write the result. We consider each component separately and use the time shift property. Please see the formula. First, we will write the constant, then the delay, and finally the transform of the non-delayed function. In this case, we don't really have any delay, so what remains is a simple unit step times 3tp. Let's write all the remaining components in a similar way. Most tasks of this type will probably require writing the result on one fraction line and segregating it by powers of z. So let's do that here too. I would like to remind you that the denominator cannot remain in this form. In nominator, if z to a given power occurs more than once, it must be taken out of brackets or summed if possible. And this is the final result. The order of the powers does not matter. What matters is that each power of z appears only once. The content of the task can also be written using a brace. You can see an example. You can try to draw this function. Then you will see that it is the same task as previous. However, drawing the function r of ntp is a waste of time. It is better to write the analytical form. The principle is simple. You need to add a function with such delay when it started, and then you need to subtract this function with delay when this function already ended. If the task were a graph, we could also write this formula. All you need to do is read the formulas of individual functions directly from the graph, without the need of decomposition. I call it the analytical method. However, there is a serious disadvantage of this approach. There are a lot of calculations to do, so it's easy to make a mistake somewhere. There will be no prescribed method in the content of the task. You can choose any method, and you can also try to calculate it by definition. However, if we have a function written using a brace, this analytical approach will be the fastest. I won't solve it now, but I encourage you to try to solve it. The result should be the same as before. Please also expect tasks where a simple function with the lies is given. For example, here I also assume that you know how to solve this. I'm just showing you what you can expect. And now something easy. Calculate what should we do here? On the one hand, the property change in the complex scale z remains, but our task is missing this function. So what can we do? We can multiply this function times the unit step. I didn't mention it earlier, but in each case, we assume that the functions take non-zero values only for steps greater than or equal to 0. And now it fits the formula perfectly. The unit step transform is, for each z, we need to substitute z times e to the appropriate power. E was to the power of minus ntp, and now we need to change the sign and omit n. Another task. Calculate the transform of the function m of ntp Earlier, I said simply that to use the time shift, both brackets must be the same. It is completely correct to say that wherever the ntp variable appears, it should be in the form as in the delay. In this case, the variable appears only in power. Hence, e to the power of -3 is a constant. Now we can use the time shift property. And we have already calculated this transform. Suppose we have a function f of ntp equal to n. What is the transform of this function? I remind you that as before, we multiply by the unit step. And from the property you will need the ability to calculate the derivative, and I assume that you can calculate it for both the product and the fraction. Is it reminds you of something? If so, then very good. Tp is a constant. And we obtained the transform of the linearly increasing function, but in a completely different way. Of course, if we have n to the higher power, we should simply calculate more derivatives. Now let's consider such a function. We need to apply the subsequent properties, but the order doesn't matter. Let's start with NTP. We will use the property and the result in the proper form. Now let's start with the second part. And we got the same result. If sine or cosine appears in the task, you can assume that the Laurent transform will be given. And here, if someone is not sure, it is better to write more than make a mistake. And now the periodic function. I remind you here the formula for the transform of a periodic function. W1 of z is the transform of the first period of the function, that is, such a function. I will draw half-line components. Please note that the vertical axis shows values without TP, so the slope is equal to 1 by TP. The non-delete unit step can be omitted. And once we have the first period transform, we can easily substitute it into the formula. Each period consists of 4 samples, so here we enter 4. The last task is calculate the initial value and final value of the function which Laurent transform is equal to. Let's start with the initial value, it will be faster. There was no need to write this, just to make it clear what we counted. Since z tends to infinity, then z to the negative power tends to 0. In the case of the final value, it is a little more difficult, because we have to start by checking whether the final value exists, that is, whether the poles of the expression are exclusively in the unit circle. We need to count the poles of the function b of z. We need to check how far these points are from the origin of the coordinate system. We will calculate it using Pythagorean theorem. This is less than 1, so the final value exists. If it was greater than 1, it would be written that the final value does not exist, and that would be the end of the task. So, the final value is 0. You may wonder whether a different value can be obtained, since we always multiply by 0 anyway. Yes, when this bracket shortens with the denominator of the function. That is, if the function has a pole exactly at 1. However, if the function had a pole on the unit circle that would not shorten, then the final value would not exist. That's all I wanted to show you in these classes. Thank you for your attention and have a nice day.